Okay, so welcome to lecture 2 of deep learning. Today we're going to talk about how you actually train a neural network. And I imagine that some of this might be review for some of you, but hopefully kind of the perspective or the way we talk about the process of training the neural network might be slightly reformulated from something you've seen before. I definitely think that this slide is a nice way to characterize the process. So today, we're going to talk about how you actually train a neural network. First, we're going to start doing a bit of a review of gradient descent, SGD, high level, some optimization ideas. Then we're going to introduce the concept of a computational graph. We'll talk about backpropagation through chains and through multi-layer perceptrons. We'll talk about backpropagation through DAGs, and then we will get into the concept of, differential programming. Okay, so just again, as a bit of a refresher, when we talk about a neural network, it's usually something that follows the sort of rough structure of this, where you will have some input data X, and during training time, you'll have some ground truth for that input data. This is the thing that you want the model to learn to predict. So in this particular instance, that is a clownfish. We're asking this model to predict maybe a visual category, and that's why. And then we have some model. This is a sort of a chain of different blocks or layers of a neural network. Each of those layers will have parameters associated with them. And then once you send this input through all of those layers, you'll calculate a loss based on the difference between what the model predicts and that ground truth. And all of those parameters that are sort of going through the network, those are actually what's getting learned. And when you say getting learned, essentially we just mean we wiggle the values around in numerical space until we get something that is at least reasonably close to optimal based on a set of data that we actually have access to. Cool. So essentially what you're trying to find is some optimal set of theta that minimizes that loss function over all of your available data set. Now, when we talk about gradient descent, here, finding that sort of optimal set of parameters, what we often will talk about is that that's going to be the set of parameters that is optimal for some cost. In this particular sense, that cost function is the sum of the loss over all the data points in our training data set. And then how do we actually fiddle those weights around? What's the mechanism? That's really just using optimization to try to find those optimal parameters for that cost function. So what's the knowledge that we have about J? Well, first, we know that we can actually evaluate J of theta for any given theta. So this is something that we can actually evaluate, right? You can calculate the loss over a training data set or a test data set. We also know that we can evaluate the gradient of theta. This is sort of first order optimization. You might sort of take some approximation of the gradient based on a specific point, and you can evaluate that as well. And additionally, we can also do something like evaluating second order optimization, where you could actually calculate the Hessian. In practice, this isn't something that we often actually do. Usually, we really just focus on that first and then that first order optimization, where we're just looking at that linear approximation to the gradient at a given point. And then what is gradient descent? So if you're trying to find this theta star, that's this optimal value, what you're going to do is you're going to start somewhere on what we call the loss landscape, or the surface that represents that cost function. And then you're going to move in the direction of the gradient, sort of the maximal gradient, and take steps over your data. And so for each of these, you'll start moving sort of in that downward direction on that loss landscape and eventually find a minimum. Now, of course, you might note if this loss landscape is non-convex, if it's quite complex and maybe has multiple minima, this may not be guaranteed to be the global minimum. It might just be a local minimum. And how bad that local minimum is relative to the global minimum, often we don't know. So if you assume you're taking a single iteration of gradient descent and trying to find sort of better parameters, what we'll do is we will start with our, kth step of those parameters theta, and then we will define some learning rate, in this case eta, and that's going to say how far we're going to step in the direction of that gradient. And then you calculate essentially what is the direction of change that will optimize that loss or that cost function. So now what you do is you take the parameters of your model and you move them in the direction of the sort of maximal slope of your gradient with some sort of learning rate step value. And that gives you the update to your parameters. Now, this might be something that you could reasonably calculate over all of your existing training data. You'd like to ideally minimize the overall loss function, which would be some sum of the individual losses over every single example in your training data. But realistically, this is often not possible to calculate, mostly just due to the time, the computational complexity, especially in this day and age when data sets are getting larger and larger. So, you know, when I started in machine learning, we were lucky if we had sort of ImageNet scale data sets, like 1 million images. Now we're dealing with image data sets in the billions and text data sets even larger than that. So instead, in stochastic gradient descent, you assume that taking the gradient over some subset of your data is a reasonable approximation to taking the gradient over the entire data set. So here what you do is instead you compute a gradient on a subset of the data at any given point, and we call this a batch. So if your batch size is 1, what that would mean is you would actually update your parameters after seeing every single example in the data set. You can imagine that also might be kind of suboptimal in terms of the computational complexity of doing those updates. If your batch size is n, where n is the full set of data, then this is just standard gradient descent. But of course, it might be possible this isn't easy to fit into the memory of your GPU, or might just be really slow, computationally intractable. So also, if your gradient direction is kind of noisy relative to kind of averaging over all of the examples, which is standard gradient descent, this is pretty normal, right? So taking a batch, you're not necessarily guaranteed that that gradient over the batch is going to match the gradient over everything. And actually, in a lot of the data that I work with, where we have things like significant imbalance over the types of categories we're interested in predicting, this sampling can have a pretty strong effect in terms of how stable that gradient is, right? Because potentially you have some categories that are not seen for multiple batches at a time, and then you see them, and at that point, it actually massively shifts your gradient. So this instability is actually often related to how kind of uniformly distributed your data set is. But there are advantages of doing that stochastic gradient descent. First, it's faster. It's been shown to approximate the total gradient even with small samples. And that noise, it's actually an implicit regularizer. So one thing that can be a benefit of stochastic gradient descent is it can actually kind of bounce you out of local minima and help you sort of reasonably find closer to what might be a global minimum. There are disadvantages. Like we said, there can be high variance, there can be unstable updates, and I've found experimentally that these updates are more unstable the more unbalanced your training data set is over the set of categories that you're interested to predict on. Cool. Any questions about SGD? How many of you have seen SGD before? Okay. That's what I thought. So this is hopefully a bit of a refresher for most of you. We also want to introduce the concept of momentum. And this is something that we might sort of implement within our loss, or within sort of our gradient descent. So essentially, the idea of momentum is kind of the physical idea of momentum. If you put something heavy on a slope, it will gain speed as it rolls down the slope. And what we do when we think about momentum in gradient descent is we essentially are biasing our gradient steps to continue in the direction of the previous update. You're giving it that momentum based on its past direction of movement. And so here what that looks like is you're essentially just adding in, again, this parameterized by alpha momentum term that is capturing the direction that you moved in the past. And this can actually help or hurt. And the strength of that momentum, that alpha, is a hyperparameter. A popular example of this type of momentum in a gradient, in gradient descent is Atom. If any of you have heard of sort of the Atom optimizer, So this is something that is pretty commonly used. But how this might actually help or hurt, so here, this is just looking at optimizing for something that is quite sharp. And you can see that if the momentum is 0, you'll kind of roll sort of steadily towards that maximum. If you actually have a momentum of 0.5, you're getting to that minimum much quicker, right? Maybe about half the time, the number of sort of training steps. But if your momentum is too high, you sort of start bouncing past. And then you have this almost oscillation and wiggling that happens as you're trying to find that minimum, and it ends up taking longer to optimize your function. And there's like a really nice blog post on momentum that has some really fun interactive capacity. If you guys are interested, the link is down here. It's from back in 2017, but I found this really helpful for building intuition. Cool. So talking about sort of loss landscapes, which of these are differentiable? So raise of hands. Give me one that's differentiable. Yes. The first one, yeah. The top left. Yes, thank you. Right and left, still hard for me. Yeah. Yeah, the third one, exactly. It's flat, but it does have a derivative, right? So yeah, exactly. These two are differentiable. So now, which of these have defined gradients in PyTorch? Raise your hand. Yes. Yes, all of them have defined gradients in PyTorch. That's because PyTorch has autograd, right? It has this nice mechanism that helps us calculate gradients for any function. Which of them would be hard to optimize over? Yeah.
Second one?
Why?
This has got multiple local minima.
Yep, multiple local minima. So it might be, you might end up, depending on where you start, not in the global minimum. Yeah. Yeah?
The third and the fourth, since they're both flat.
The third and the fourth, since they're both flat. Yeah, so the third one is just flat everywhere. Essentially, there's no signal in terms of the gradient. The fourth one, it's flat everywhere except for discontinuity, but anywhere on the actual graph, again, you have no signal. Yeah?
Then the fifth one as well, because the learning rate should be very, very small, otherwise we're just going to diverge.
Right, so this one in the center of the bottom, this is also difficult because the gradient is very steep. It's very, very high as you get close to the minimum. And so the challenge there is that as you kind of get close to that minimum, the gradient is really large. So then it's going to bounce you somewhere really far away. So essentially, it's really difficult to actually ever hit the minimum because of what we call exploding gradients. Yeah, so definitely. And one kind of nice intuition around kind of easy versus hard to optimize, you can kind of think about flowing water. So, you know, in this example over here, you would actually, no matter where you started, you would actually end up getting to that minimum because essentially you can think of water kind of flowing. No matter where it came from, it would sort of still get to that middle. Of course, that really only helps you thinking about kind of, is it minimizable? So that really is only filtering out this one that has multiple minima. So one thing that's true is that most existing popular neural network components will kind of exhibit certain properties. So like we said, these would be hard to optimize. But now I want to go through sort of what these different landscapes would look like, kind of the pros and cons of them, and then we'll get into some high-level intuition and talk about where the field seems to be going in terms of the types of loss that we're calculating. So something like this is like maybe the simplest case. This is a case that if you're a theoretician is really great because you can assume convexity. You have a single minimum, all the gradients point to it everywhere, and the gradient will gracefully go to 0 as the minimum is approached. Here, we have discontinuity, but it's well defined in terms of the derivatives on both sides of that discontinuity, and this is not a problem at all for PyTorch. Here, even if this is not completely flat, which you can see here it isn't, it's what we call a vanishing gradient. The progress would be really slow. And noise in your sort of batches, for example, might end up dominating over the signal. So this would be very difficult to optimize. Here, this one, just 0 gradient everywhere, basically completely uninformative as to how to make progress. And so it's really difficult to ever hit any low loss region. There was a question? Yeah. Oh, yeah, sorry. Sometimes I assume something is intuitive and it's not, so thank you so much for asking. So this is like for different sort of parameters. Like all of these are single versions of parameters, right? So this is now looking at that plot. And then now here, this is optimizer steps going from 0 to like 100. So assuming you're starting from the top, and it's basically stepping through, assuming this was your loss landscape and you had some sort of standard learning rate, where the model would actually sort of move throughout gradient descent, or throughout stochastic gradient descent. So in this case, there's no signal, it just doesn't go anywhere. Whereas in the previous slide, or like this one, for example, you might start out over here, and it might bounce across and then go back and forth, but it will actually sort of eventually find that minimum. Thanks for the question. It was a good one. Yeah, so zero gradient, this is what we were talking about in terms of instability. This one has what we call an exploding gradient. The gradient goes to infinity as the minimizer is approached. So you have really unstable updates, and you can really overshoot. It can be very difficult to ever actually hit that minimum. And then here, when we're talking about multiple local minima, where you initialize matters a lot. This is often, one way that people handle the fact that many of our loss landscapes are not guaranteed to be convex. We're not guaranteed that they only have a single local minima. This is why you might, for example, try experimentally a bunch of different random seeds and try to then select a model that ends up looking better. And the variance in your performance based on different random seeds will tell you something about kind of how unstable your loss landscape is. So there's a couple things that we wanted to bring up. Yeah. Well, so PyTorch can make anything differentiable. That doesn't mean it will be easy to optimize. So for example, that one that's flat, like it's differentiable in PyTorch, but that doesn't actually mean that it's going to find a local minimum because it doesn't exist. So it's computationally possible to calculate a gradient there, but the gradient will still be 0. So essentially PyTorch and AutoGrad, they mean that even if you take something that would traditionally be non-differentiable, you can still calculate derivatives in PyTorch. So we assume things like directional derivatives around discontinuities, but that doesn't actually mean that every loss landscape is equal. That's kind of what we're getting into here, is sort of these ideas around what makes a good versus a bad loss landscape. Does that make sense? Cool. Okay, so one thing that we wanted to bring up was this idea of an evolution strategy. So these are sort of gradient-like. They find locally loss-minimizing directions in parameter space. And the way that they do that is they sample small perturbations around your existing parameter values and then move towards the perturbations that achieve lower loss. So for example, you could take some sort of perturbation or error that's normally distributed, and then when you're actually calculating your values, you calculate them of the loss function plus some amount of perturbation in that normal space. And then when you're doing your updates, now you have kind of this kind of almost robustness that comes in. And it will actually successfully minimize even something that looks like this. So here, even if we started up here in this sort of non-minimal situation, because we're kind of perturbing the values of the function, it might bounce us over into a better value just by sampling this cost function, these different things. So this is something, these sort of evolution strategies is something that sometimes people will take into account. And then another important one is this idea of gradient clipping. And this is a mechanism that helps us with basically peakiness or pointiness in our loss function. So we'll successfully minimize this function. And so here, it's quite simple. If the gradient gets too high, above some large value, you just scale them back to that value. So you essentially just put like a clipping filter on top of your gradient. And this is a useful and commonly used hack. So here, essentially what you do is you just calculate the change in your parameters, and then you move in the direction of that maximal change, but clipped to some maximum value. So you won't let your model sort of move too far in any direction. And this then helps us, with not oscillating back and forth across something. So what then is important in a loss function? So a few things that are sort of consistently showing up. One, though this is of course not required, everywhere continuous. Another one, everywhere differentiable. And the third one would be everywhere smooth. So one of the most commonly used nonlinearities is ReLU, and this is something that is everywhere continuous, almost everywhere differentiable, but it's not everywhere smooth, right? We have this kind of sort of kink in it. Now, recently, there's been a lot of work that will instead use something like GILU, which is a Gaussian error linear unit. And this one essentially just takes the parameters times phi of the parameters, where this is the cumulative distribution function for the Gaussian distribution. It looks something like this in 2 dimensions. And this one is everywhere continuous, everywhere differentiable, and everywhere smooth. The important thing I want to point out here is that we can kind of agree that these 3 things might make optimization easier. And even if we don't precisely know, experimentally or theoretically, which properties are needed for training neural networks, trends do seem to be moving towards functions which satisfy all 3. So things like this GILU. Any questions about optimization in SGD? Yeah. So evolution strategies? Yeah, essentially they're, instead of always moving in the direction of the gradient, you just randomly sample around your current parameter values, and then you move in sort of the random direction that maximizes or that minimizes your cost. Essentially, it's helping you maybe handle things like vanishing gradients or like some of these sort of parts of your loss landscape that might be not actually functional to optimize super efficiently. And I think you can almost think of it like one intuition is it's almost like regularization in your loss, if that makes sense.
Also follow up, how common is it that people use like everything together and stuff?
Yeah, I mean, I think everything's a bit of like a big like soup pot these days, right? Like there's a lot of these different experimental tricks. Some of them, even if they seem quite different, almost seem like they achieve the same ends when you talk about the experimental performance. I would say that a lot of the really top performing state-of-the-art models on different types of benchmarks are often ones that incorporate a lot of these tricks, different sort of hacks and mechanisms to try to get a little better at finding some maybe slightly better optimum. But I don't think we actually have a really great recipe for, given a certain data set, given a certain architecture, what is the right way to optimize that architecture? Yeah?
Can you please explain how ReLU and GILU relates to this question of what is it for the functions?
Yeah, so again, I'm not saying here that like GILU is much better than ReLU all the time, because that's not necessarily true. It's just pointing out that sort of the trend in these different loss terms for neural network training does at least seem to be moving towards moving away from functions that don't satisfy all 3 of these. But again, like we don't necessarily know, or we haven't sort of decided as a community or sort of even gotten close to some sort of theoretical guarantee as a community as to what is the optimal mechanism. Yeah?
Are these loss functions? Like, are these like activation functions?
These are activation functions. Yeah. Sorry.
Should loss functions also not be negative?
Well, it depends on the way you've set up your loss. You definitely can have loss functions that will have negative values. That depends, right? And I guess what you're saying is if you're trying to minimize a cost, you want the gradients to sort of move in the direction of that, but that's not guaranteed if you can't guarantee the loss landscape is convex everywhere, right? There'll be parts where it goes up and down. Yeah?
Is there any issue with having a non-monotonic function?
A non-monotonic sort of activation function or loss function?
Activation function.
I mean, there definitely exist, like in theory, activation functions that are non-monotonic, but I don't think that they're often widely used. I mean, it seems to make sense, right? It's not, right? Yeah, it has this part where it dips down right here. Yeah. But then this is kind of the question, right? Is it better to be smooth or to be monotonic? And that's kind of where I think the jury's a little bit still out. But yeah, I guess we could put monotonic here, but I feel like these three are the ones, at least from my perspective, that seem to be kind of captured most consistently across the activation functions that people tend to use or are moving towards. Yeah.
I was wondering for the perturbation, can you talk about it from like a numerical mathematical equation? What are the strength of levers that affects that, like making it the magnitude bigger or smaller, and also from the application sets, if you're looking at a data set, what would be
You mean this?
Yes.
I mean, so definitely those parameters are something that you would need to experimentally find optimals for any given data set or problem, right? Like it's not like there's some sort of universal ideal here. And I think it'll probably depend a lot on which data set, which architecture, for example. So I don't have any big rules of thumb for you there. Though I would say one sort of generally good strategy is you take a paper that used it and you look at the values they used and you start there, just usually because they've already done it, right? They've already done it to sort of define their sort of optimal parameters, and sometimes those can be really far off for a new data set, but it's often not a bad strategy to at least start with something that has trained for someone in the past. Okay, I'm gonna move on. Great questions though, guys. It's much more fun for a professor when people are engaged, so it's great to hear from you. Cool, so I'm gonna move on to talking about computation graphs. So we're gonna try to move to thinking of this all from this perspective of differential programming. Essentially here, you're talking about a computation graph. Here, this is something like a graph of different functional transformations. Each of those functional transformations is a node in the graph. And then when you string all of those together, you can perform some useful computation. So intuitively, maybe this is some sort of decision tree, right? That's a very simple version of a graph of functional transformations. So maybe I'm saying, like, all right, I'm going to try to make it to the classroom. So I'm going to go into a building, and then maybe on the right, you've gone into building 45, which is correct, and on the left, you've gone into building 32, which is incorrect. And then sort of there's these different decisions you might make based on the values of your input at any given time. So if you did go into building 45, then you could maybe take the elevator or take the stairs. And that decision over what action you'd take could be a really, really simple heuristic version of a functional transformation, right? Because you're transforming your inputs to some output. Of course, the kind of what we actually sort of see here when we think about machine learning systems is each of these maybe blocks are something like a layer in a neural network or even an entire neural network, right? And there's nothing that says that what the size of these are, what any sort of restrictions when you're thinking about it really from this high level perspective of a computational graph. So deep learning primarily deals with DAGs. These are directed acyclic graphs. So directed means the information only goes one direction on any given edge. Acyclic means you don't have loops or cycles. And we also assume that every single one of these nodes is differentiable. Though we did just say that using PyTorch you can calculate a derivative for almost anything, so that becomes less of a hard constraint. So if we now sort of think about this from the perspective of, for example, a really simple multi-layer perceptron like we talked about on Thursday, here you can kind of think of that now again as one of these directed acyclic graphs. You have your input x, you send that through this linear layer, which is kind of one node in the graph. Then that gives you some hidden unit z. You send that through an activation function or a ReLU. That's, again, some computation that takes an input and changes it to create an output. Now another hidden layer h, hidden state h. And then you take that and run it through another linear layer, and that gives you your output y. So, even an MLP, easy to represent as a computation graph. So now, let's talk about what a forward pass actually looks like and what's required to calculate a forward pass. So in the simplest sense, for any model, right, for any set of parameters, for anything within that function, you take in some input value, you take in some theta, which are the parameters of that component or of that sort of function, and then you calculate you map through that functional transformation the inputs, the parameters, and you get out the outputs at that layer. So that's a forward pass for sort of any type of computational function. Now you can have multiple layers, right? This computation graph, for example, could represent an MLP. Where now you have your inputs, you have your inputs and your parameters for that first component, then you get those, that's an output, that becomes the input of the next component, et cetera, et cetera. And then, at the end, maybe you have something like this loss that you use to calculate your cost. So then when you're thinking about learning, now here you have, in order to sort of calculate this learning, that's where we think about computing the gradients of the cost with respect to all of those modeled parameters that happen all the way through the network, right? And so by design, every single layer will be differentiable with respect to its inputs, and therefore this is actually possible to compute. It is possible to compute that gradient with respect to all of these model parameters, so you can figure out how you need to update those model parameters to move to a more optimal cost. Okay, so a bit of an aside, just in case any of you are not brushed up on your matrix calculus, because this will show up a lot. We're going to be doing a lot of matrix multiplications in this class. Hopefully this is super review for all of you, but just a reminder. So we're going to assume that our inputs are, for example, column vectors of size n by 1. Now, if we define a function on that vector, y equals f of x, if y is a scalar, then the derivative of that output with respect to x, the input, would be a horizontal vector, where for each element of that vector, you're getting the partial derivative of y with respect to that sort of first element or second element or third element of x. And then that is a row vector of size 1 by n. If y is a vector of m by 1, then we assume the Jacobian formulation of the partial derivative of y with respect to x, where now you essentially end up with something that's a matrix of size m by n, so m rows, which is the sort of size of y, by n columns is the size of x, and each element of that matrix will be the partial derivative of that element of y with that element of x. Now, if y is a scalar and x is a matrix, so for example an image of size n by m, then the partial derivative of y with respect to that matrix x will be a matrix of size m by n, where now here each component corresponds to that relevant component of x. And note that by taking that derivative, we flipped the rows and columns, so it's been transposed. And according to Wikipedia, the three types of derivatives that have not been considered are those involving vectors by matrices, matrices by vectors, and matrices by matrices. Notation is not widely agreed upon. We're not going to see any of this in this class. Cool. So, chain rule. For the function h of x is f of g of x, how do you take the derivative? Who remembers the chain rule? Yeah.
X times the derivative of g of x plus f prime of x times g of x. You basically just.
Okay. I don't think that's right. It's all right, man. It's all right. Okay, go for it.
By gx prime with the f prime of gx.
Yes. So the derivative of f with respect to g of x times the derivative of g with respect to x. Yeah. Good job, dude. Way to go for it. No one's going to judge anyone for getting something wrong in this class. All right, so then actually if we write this out as z is f of u and u is g of x, then you can kind of write it out this way, right? So essentially you can write this out as the multiplication of two partial derivatives. So that means that p would be the length of vector u, and m would be, wait, what the fuck is p? What am I talking about? All right, essentially what we want to get at is what size are each of these things. So who can tell me what the sort of shape of the partial of z with respect to x would be when x equals a? I can give you one freebie if it's helpful. So, right, if we say the size of u is p, the size of z is m, and the size of x is n, then the partial of z with respect to x would be an m by n matrix. So what size would the partial of z with respect to u be? Yeah. M by p, which this is really confusingly written. I'm going to rewrite this next year. P is the length of vector u equals the size of u is confusing. But yes, m by p. And then what's the last one? P by n, exactly. Cool, so therefore, if you said sort of the size of z is 1, the size of u is 2, the size of x is 4, then essentially what you're saying is this derivative would be essentially equal to this product of two matrices, though one is really a vector. All right, we're bringing this up because we will see a lot of matrices times matrices in the next bit. So that's the end of our little bit of a vector calculus or matrix calculus reminder. So let's talk about backprop. How does any of this become possible? How do we calculate the update in those parameters? Essentially what we need to calculate is the partial derivative of j with respect to, for example, those initial layers in the model, theta 1. So by the chain rule, you can essentially factor it out, and you can kind of map that back through all of these different layers. So the inputs and sort of outputs of x as it goes through all these different layers. And if you need to calculate sort of the partial derivative of j with respect to that second layer's parameters, you'll note that it's the same essentially, but the thing that's different is here, just these last terms are different, but everything for those two are shared. And this is really the trick, right? We could separately compute all of the derivatives using the chain rule, but because these terms in the gray box are shared, we only need to compute them once. So backpropagation is a pretty simple algorithm for propagating shared terms through the computation graph. It's basically an efficiency trick, but it's one that makes it computationally practical for very large models to be able to actually calculate these gradients. So if this is a forward pass, we're sending data forward through the network and then computing the outputs and calculating the overall loss. Then a backwards pass looks like this, which is that we send our error signal, the gradients, backwards through the network from the outputs and the loss back to the inputs and the parameters. Does this make sense? Cool. So what does a backwards pass look like for a generic layer? We're going to keep track of two kinds of arrays of partial derivatives here. So first, L is the gradient of the layer outputs with regard to the layer inputs. This will be a matrix, right? This is the sort of what way does each of these parameters need to change to sort of move in the maximal direction of optimization. So here, So here, this is essentially a matrix that's just telling you which way would these parameters optimally move. And then second, we're going to keep track of G, and this is the gradient of the cost with respect to the activations, and this will be a row vector. So this is basically saying, essentially, what's the partial derivative of J with respect to X, with respect to that input. So now if we want to update the parameters, that's actually really easy if we have both L and G. Essentially, it's just a multiplication, right? You have G out, and you multiply that by L of theta, and that matrix multiplication actually just updates your layer. That tells you which way to move. And so now you take your parameters, and you change them by your learning rate multiplied by that update. So how do we actually get L and G for each layer? So L comes from that derivative function of the layer, which we assume is provided, right? We assume for any given layer that it is differentiable and that we have a function that lets us take that derivative. And then G is something that can be computed iteratively via recurrence, right? So you take the input gradient will always be equal to the output gradient times that L for that layer. So this is essentially the backpropagation of the error signal back through the model. And then all of this machinery is used to then compute parameter update directions, right? So which way do we need to go? So the full algorithm, forward then backward. First we're moving forward, then we go backward, and then we update and repeat. And this is essentially how you train a neural network, right? You do a forward pass, calculate loss, you take that loss, propagate it backward, update all your parameters, and do it again and again and again until you've sort of found some likelihood that makes you think that your model is finished training. Often we'll do this, we'll talk more about mechanisms for this later, but it's often using something like a validation set and looking for some sort of plateauing of change on that validation set. So if we're doing backpropagation, now what we've got here in the next sort of set of slides are essentially like cheat sheets for a lot of this stuff. It's really just intended to be a pretty nice resource if you need to kind of refer back and think about how you might need to implement some of these. So now a forward pass through some hidden layer. So now we have the layer before and the layer after. We take this input, we run it through the function, and then we have this output. Now, when we're doing that backwards pass, we're taking the derivative with respect to the output. We take the partial derivative with respect to the input. And then we also are calculating how we're taking the parameters in, and then we're calculating the change to those parameters going out. So this means that layer L, for this explicit layer, we have, so all the inputs are going in with the full lines, and the outputs are always in the sort of dotted lines here. So the inputs are then the previous layer's output, the change in the parameters with respect to the next layer, and the current parameters. And then the three outputs of every layer are going to be the output, right, running through the function, the change in the parameters with respect to the previous layer, and the actual update to the parameters. And then, so given those inputs, we just need to evaluate those three things. And this actually makes kind of training happen. So now if we take a summary, forward pass, we'll compute the outputs for all the layers. Backward pass, we compute the loss derivatives iteratively from top to bottom. And then the parameter updates, we compute the gradients with respect to the weights, and then we update all of those weights. Okay, so now what we actually do is we do this over batches, right? We're not doing this for a single data point at a time. And technically what that means is we want to minimize the average cost over lots of data points, the entire sort of size of a batch. And in this day and age with very large memory GPUs, that batch size could be thousands of data points at once. So then the gradient of the total cost is just the average of all the gradients of all the per data point costs, right? Because when you take a derivative, it can move inside the sum. So pretty straightforward. So now, if we actually have this as a linear layer, let's talk through what that looks like, because it turns out everything gets really nice and simple. So first, forward propagation is quite simple. If we have a linear layer, the sort of weights of that layer are just a matrix. So now, if you want to calculate the output, you just take that matrix and multiply it by our vector of inputs. So pretty straightforward. if you want to calculate backpropagation to that input, this is essentially the input gradient is going to be the output gradient multiplied by the update to those parameters with respect to the input. So essentially, that just looks like this, right? This is just that matrix that we've defined that represents the direction that you would want to move in for those weights. And then we look at the component of the output with respect to the jth component of the input, the ith component of the output with respect to the jth component of the input. It turns out that that is wij, and so that actually means that this is really just the weights again, right? So this is really nice and simple, right? You just multiply sort of in the opposite direction, you multiply the gradient by the weights to get the gradient coming in. Cool. So your forward and backward pass are just multiplying by your weight matrix, just in a different order. Pretty nice. And finally, now let's see how we use those outputs to compute the weights update equation. So how do we actually do that backprop through to the weights? So that looks like this, right? We're trying to take the partial derivative of the cost with respect to those weights. And so that's going to be the output gradient multiplied by this partial derivative. If we look at the parameter wij and look at how that parameter changes the cost, only the ith component of the output is going to change. So this means that essentially you can break this down through this kind of simple, almost decomposition. And you end up getting this because of what we just pointed out. So essentially, the partial derivative of the output at that ith component with respect to the weights matrix, the corresponding element, ij, is actually just going to be equal to the input of j, right? And so that means the following. Essentially, when you want to calculate the update to the weights, all you're doing is you're multiplying the input to the function by the output gradient. Again, it's a really nice kind of simplification that comes out just because everything is linear. So then when we actually want to update the weights, you're literally just taking eta and transposing this and multiplying it. They're adding it in to the weights. Any questions about this sort of very nice, simple reformulation that gives us essentially a bunch of matrix multiplications? Yes?
Do we have enough time? Can you work through like a small example with the computation graph on a board or something?
So at the end of the lecture, I actually do have an example of that. And so either we'll get to it at the end, I'm a bit worried about time, or it's in the slides, and so you can actually work through it, and there are the solutions at the end. Sounds good? Cool. All right, so cheat sheet for a linear layer. The output is equal to the weights times the input. The gradient in is equal to the output gradient times the weights. And the update to the weights is equal to the input times the output gradient. And then you actually do that update based on adding in that basically direction you want to move in multiplied by your learning rate. So now let's look at a whole multi-layer perceptron. What happens when we put all these operations together? So first, you have some linear layer. Then you'll have some ReLU, some activation function. In particular here, we're talking about ReLU. Then you have another linear layer. So now this will be sort of weights 1, weights 2. And then you calculate some loss based on the difference between your output and the ground truth. So now to do a backwards pass, you essentially assume a slight change in convention. This will kind of clarify this nice connection between forward and backward directions. So instead of representing gradients as row vectors, we're going to transpose them and treat them as column vectors. And then that backwards operation for the transposed vectors will follow from that matrix identity that AB transpose is B transpose A transpose, right? If you remember sort of basic matrix math. So essentially, this then reveals this interesting connection between forward and backward. So backward for a linear layer is the same operation as forward, but with the weights transposed. So here, now you're going backward. You get, again, weights transposed times the gradient. And then, this is an interesting thing. A ReLU wouldn't be a ReLU on the backwards pass, right? Because you don't want to sort of pass them through a ReLU. Essentially, what you need to turn it into is like roughly like a gating matrix. This will be parameterized by the functions of the activations from that forward pass. So these would be sort of like A, B, and C, sort of the activations that you had sending those weights through the ReLU on the forward pass. But what this is doing is making sure that you're not passing gradients for the components of the weights that corresponded to the parts that were sort of like in that zero part of the ReLU, right? You don't want to send gradients for parts that should be masked out. Yeah?
Why is that matrix diagonalized?
That's just so that it's operating on each element sort of independently, right? Cool. And then, now you can kind of mask the values of the gradients, make sure you're not sending gradients for things that are going into that zero, that negative part of the ReLU. And then essentially what this means is that Backprop is still a linear model, right? Because even that ReLU, this is still a linear operation that we've taken. And there's kind of a cool intuition. Phil told this to me, and I really liked it. If you're thinking about a loss landscape, no matter how complex that loss landscape is, if we're taking a first-order approximation of a derivative, essentially what we're doing is we're fitting a plane to this complex curved loss landscape, and then we're moving in the direction of the plane. So by definition, it must be linear, right? We're moving on a planar surface, even if the actual underlying loss is not planar. Make sense? Cool. So this means that forward and backward for a linear model is actually all just one really big kind of flipped out linear model, right? You can treat the entire thing as a single iteration as just one big linear model. And it can kind of be thought of as a single forward pass in a way, even though the actual kind of forward pass is only the first half and the backward pass is the second half. Yeah?
Comparing forward and backward path, you showed that to compute the backward path, you need to have the X in at each layer. So it means that you need to have in memory all the layers, what is the value of the embedding. Whereas in the forward path, you don't need it, as you only need it for you can discard the previous embedding, for instance, with your image of bird, or you can, once it has passed through the first layer, then you can just erase the bird from your memory as you're only going forward. Whereas in the backward pass, it means that you need to save all of them.
Yes. So you do need to save the intermediate representation so that you can efficiently compute backpropagation. That's true.
So there's not really a symmetry between the forward and the backward path size.
No, they wouldn't. But I mean, you can actually even see that here, right? Like there's this kind of asymmetry in where the information is flowing. Does that make sense? Yeah. Yeah.
Is there a specific reason why we don't say like pi is there?
Oh, that was just for simplicity here. So yeah, in practice, there would be bias terms floating around everywhere, but we just wanted to kind of capture the intuition. Yeah. Mm-hmm.
When we're going back through our ReLU layer, are we do we need to know the pre-activations? Like, do we need to have that in memory?
You basically need to save off what the value of the activations were for each component of your input. And you keep those in memory, and then you build that sparse matrix that lets you actually kind of gate those going back through. Yeah, cool. Okay, so let's move on to talking about DAGs. So what if your DAG isn't a chain, right? And actually, this is pretty common. We often have connections within our machine learning models that are not just chains. For example, sort of sharing weights or splitting weights or having, things kind of come together, be concatenated from different heads or being sort of split into different sort of objectives. So let's talk about what this actually looks like. So there's actually only 2 operations that you need to make everything we just talked about work for any arbitrary directed acyclic graph. And those are merging and branching. So assuming you have some merge, where here, and that merge could be a lot of different things. It could be addition, it could be concatenation, what have you. You have, some components, some functional components that you're merging together to move forward through your directed acyclic graph. Now, if you actually need to propagate a gradient back through that, essentially, you just need to make sure that you track the gradient with respect to the correct input variables, right? So if here, you just only pass the gradient that corresponds to the sort of x superscript a, and on the other path, you only pass the gradient that corresponds to the components of that other part of the path. Similarly, if you're branching, so now you're splitting up your information in some way, or even just duplicating it. Now, if you're propagating a gradient back through that, it's as simple as a sum. You just sort of take the gradients from both and you sum them and you send that back through that input. Cool. So there's a much more detailed derivation in the lecture notes if you're interested. So now let's talk about what this means for parameter sharing. So say you have some chain, and now you have, the parameters are sort of separate for each component of that chain. You might instead have something where those parameters are actually shared across those different components. Maybe you're reusing parameters that were pre-trained on ImageNet or something, and you're using them in multiple parts of your network. There, again, you can actually just kind of think about flipping this on its side. All that is a branch, right? So now if you're passing your gradient back through that branch, you just need to be summing the gradients that are coming in from these different branch dimensions. So parameter sharing, summing gradients. All right, so towards the end of the lecture, now I want to move on and talk about this kind of meta concept of what differential programming is and maybe why neural network training is essentially just differential programming. So when we think about deep learning, generally, we think about it this way, right? You have some network, again, a DAG, and then you define sort of these forward and backward passes through that network. Differential programming takes the same perspective, but now we basically just are actually programming that model. And this is really what all of these different existing languages, PyTorch, TensorFlow, if anyone still uses it, JAX, these are all basically libraries that enable us to really efficiently do differential programming. So deep networks are popular for a few different reasons. First, they're easy to optimize, right? Everything is differentiable. Second, they're compositional, right? It's essentially like block-based programming. And so differential programming sort of surfaced as an emerging term for general models with those properties. These tweets are a bit old now, but I still think they're funny. Jan LeCun said, "Deep learning has outlived its usefulness as a buzz phrase. Deep learning est mort. Vive differential programming." Essentially, even years ago, this was kind of like, maybe this is the new buzzword for what we're talking about here. Tom Dietrich, who is significantly less splashy in his tweets, said that deep learning is essentially a new style of programming, differential programming. And the field is trying to work up what the reusable constructs in this style are. And there are some that we actually know. Some of these blocks have been kind of well-defined. Things like convolution, pooling, LSTMs, GANs, VAEs, memory units, routing units, et cetera. So, this is kind of taking that perspective. This is a paper from 2017 called Neural Module Networks, where essentially here you can see that there's these different components of the model, and some of them might be sort of architectural, and some of them might have parameters that are learned or not. So, you're sending in something like, where is the dog? And then maybe that gets routed to a parser, and that parser might not be learned at all, right? It might just be a standard parser. So that component might not have any differential or parameters that are actually being learned. But then potentially there's a CNN down here that's parsing the objects that are seen in an image, and that might actually be something that you have updates being propagated to from your training data set. And there's an interesting blog post from Andrej Prkopathy that kind of talks about this as what he calls software 2.0. Essentially here, he's saying that software 1.0, which is the software we sort of had originally, where everything is defined, that might be just that little red dot. Software 2.0 is actually defining a space of possible sort of software systems, and then you're actually optimizing within that space to build the system that you need to solve your problem. So here, instead of thinking about this DAG where every component is actually differentiable, or every component is differentiable, where every component is learned, instead you might have a bunch of the components of your system be explicitly programmed by a human. A really obvious example of this is we often explicitly program the normalization values that we want to use for natural images directly into the pre-processing of our data, right? This is something that we just define. We don't learn what those normalization values should be. And then there are these other components where this part is actually programmed by backpropagation. So for example, programmed by tuning the behavior to match the training examples. And the cool thing is, because we assume that every piece of this system is differentiable, you can actually optimize any node or any edge with regard to any scalar cost. So here, you could think about calculating how the cost would change when the weights of the specific yellow function change. You could also think about looking at how the cost changes when the input data changes, right? You don't actually need to specifically do this for weights. Yeah?
So is this how we use, or create a metric that can determine what might be good for a human to train versus the computer to train, or is there another qualitative or empirical metric that we might use?
So, a big question. So he was asking if this is something that helps us sort of build metrics around what maybe we might want to optimize via data versus what we want to just define directly. I think experimentally we often kind of find those things out for different applications. What parts is it actually good to, essentially, anytime a human is programming part of the system, it's constraining the system. And that constraint can be useful, but it could also be unuseful. I think about when I started in machine learning, we often had, it was built around, I'm gonna date myself right now, but we did a lot of what we called feature engineering, which is essentially like us building a bunch of explicit constraints into how the data might be processed to then go through a very, very simple neural network or even something more simple than that, something like an SVM. And those bottlenecks, it turned out, were not necessarily optimal, right? We were defining this, we were programming it, but it turned out our best ideas were not as good as just much more complex, larger models that were learned somewhat end to end. Does that make sense? So I think the jury's a little bit still out. When you talk about metrics, that's really where that red square comes in, right? You define what that cost function is. So you have to kind of figure out how you are going to define the loss and what that then looks like for your cost, and that definition will affect what your sort of optimals are. Cool, so let's talk a little bit about optimizing parameters versus optimizing inputs. So this is the kind of standard approach, right? This is looking at how much the total class is increased or decreased by changing the parameters, right? These are sort of all the different parameters throughout the network. This is what we sort of commonly think of. But you can also think about optimizing the input for a fixed set of parameters. So here, this could be something like how much the chameleon score is increased or decreased by changing the input pixels. And so here, now, if you think about this from sort of a way where you're optimizing maybe class logits before the softmax or optimizing the class probabilities after the softmax, the maybe easiest way to increase the probability softmax given to a class is often to make the alternatives unlikely rather than to make the class of interest likely. Whereas if you optimize pre-softmax logits, this tends to actually be a bit more stable. So what we find is if you want to actually make an image that maximizes the cat output neuron, again, we are doing this maybe pre-softmax. it might look something like this. So this is an interesting, again, blog post back from 2017, but on feature visualization. So this is telling you what a given trained model thinks is most cat-like. And this is something that you can learn. Or you can actually also do things that say, for example, make an image that maximizes the value of a neuron, J, on a layer, L. So finding something about, like using this as a mechanism to probe what the model is paying attention to. So that might look something like this, right? This is saying that like this particular neuron in this particular layer is looking for stuff that looks like this in kind of a hand-wavy way. And this is kind of the idea behind, for example, Deep Dream. I don't know if any of you guys saw this, a couple years old now, but I think these are kind of psychedelic and beautiful. And this is kind of looking at what these models, I guess, dream of. And this is also, this is kind of an idea of what's to come, but if you're kind of comfortable with the idea that you can optimize anything with respect to anything, here we're sort of looking at maximizing CLIP as a model that tries to make descriptions and images that correspond to them close together in a joint embedding space. So you want to build a text encoder and an image encoder where things that are similar semantically from text to images are quite close together in the sort of learned embedding space, that projection that you're projecting each of them into. Now, if you have something like CLIP, then you can, for example, tie your CLIP model together, the image encoder and the text encoder from your CLIP model, together with a GAN, something like a generative adversarial network, and then you can optimize the embedding, or so that input parameter that goes into that image generator, and you can figure out for a given input how to optimize this so that your output of your image generator is the thing that's closest in CLIP space to any sort of given prompt. And if you actually look at what that learns over time, you can get stuff that's kind of fascinating, right? So this is a way to actually generate an image from text. And here, you know, again, all these trapezoids are neural networks. You can plug them together. You can take the components trained in one way and use them in another way. Really, the idea is you can optimize modules with respect to all the other modules, and the world's your oyster. Cool. So what we covered today, review of gradient descent in SGD, computation graphs, backprop through chains, backprop through MLPs, backprop through DAGs, and differential programming. Any questions? Yes. Mm-hmm. So essentially what we're doing here is you had CLIP, you have this text encoder and this image encoder, and they were already trained, and now they're fixed, right? So the idea is here, the text and the image encoder, actually, we're not backpropping through them at all. They're now defined. They're not being learned. And similarly, you've separately trained an image generation model that takes in any given embedding and generates an image from that embedding. Now, that one is also fixed. So now you have a lot of parameters in a model, but all of them are fixed, and the only thing you're optimizing is this kind of, you know, hidden parameter that's going to be the input to the image generator, such that this is maximal, right? So you're trying to find this kind of z value that maximizes this with respect to that input text. Sorry? So so all the parameters here are fixed, though you are going to need to calculate how to backprop the signal back through these models to get to that one. Yeah. Yeah. Yeah, absolutely. So when I say embedding, I might also say representation. These are all terminology that we often will throw around in the machine learning community, but usually it means something like this. So you have some neural network, and we'll call them an encoder sometimes, again, just terminology. But this neural network is essentially building a mapping from a high-dimensional input or a complex input, something like an image, to a low-dimensional representation or a low-dimensional embedding of that input data. And so that might be, a vector of length 2048, for example, or 1024. Those are both sort of common embedding sizes. But really, when we talk about embedding, it's essentially just saying we've trained the neural network already. Now we're using it to give us like a low-rank representation of our data. Does that make sense? No. Yes?
I noticed in some of the slides you used loss and the others have used cost. Are they interchangeable?
No, this is me being a little fast and loose. The way we defined it is that the loss is like a function over all of the data points, and then the cost might be sort of the overall calculation of that loss over maybe all of your data or something. But I think it's a little semantic. Yeah, I think it doesn't, it's not the end of the world to sort of think of them somewhat interchangeably. Essentially, both are, you're defining some mechanism for evaluating optimality. Yeah?
How easy is it to switch between optimizing parameters versus optimizing inputs?
So lucky for us, things like PyTorch exist, and so actually this is just a matter of defining what you want to update, basically where you want to freeze your gradients and where you don't want to freeze your gradients, and that's not actually so hard to do.
Okay, and if we were to do that switch, could we use the prior word, like convert it in a way that we can use the prior word as language?
So this is where kind of that modularity comes in, right? Sorry guys, if you could be quiet. So this is where the modularity comes in, right? So we talked about here, right? Like you can have these models where some parts are programmed by a human and some parts are actually being programmed by Backprop. But you could also think of the ones that are quote unquote programmed by a human. Those might have just actually previously been programmed by Backprop, and now you're taking those weights and plugging them in. Yeah. 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 Sorry, what? Sorry, if everyone could just keep it quiet so that I can hear the questions. Thank you so much. Yeah? Is that what I would call a what? An attention block. Oh. So this is a cosine similarity. And cosine similarity is a component of attention, but it doesn't actually sort of make up all of what we would call an attention block. So the attention block, generally defined for a transformer or something, will also include the projections into the shared space where you're going to take that similarity, as well as a projection out into the space where you actually want to use the information about what's valid. Yeah. Yeah. It'll be by the end of the day today. Sorry. We were working on it in our meeting right before this, and I thought it might be up, but not quite yet. Yes? Did you have a question? No? Okay. Yes? You're going to need to be a little louder. Sorry. If we can just be quiet as we leave, thank you so much. All right.
So, could you please, what's the difference between the backprop for MLP and that? Because they're both computational graphs, right?
Yeah, so there's no difference, right? And this is where the only two things you need to take all the stuff we talked about from Backprop through MLPs and translate it to Backprop through any DAG are these, right? You need a merging operation and a branching operation. So now, essentially, they're just changed with merging and branching, and that represents any DAG. Yeah. Yes?
Is it just a different way of looking at backpropagation?
Yeah, so essentially all we're saying is that all the really detailed examples we showed of backpropagation, those were all for a really simple chain-based DAG. Is just like you have a component and it goes, and then a component and it goes. So it was all a chain. And now what we're saying is that you can actually take everything we talked about it and apply it to any structure of a DAG. Because now it's just chains where sometimes they merge and sometimes they branch, but there's really simple operations that we can use to pass the gradients through merges and branches. And so that's kind of how you expand that definition of backprop to any DAG. Yeah. Sorry, what? Sorry, I'm having trouble hearing you. Mm-hmm. Yeah. Why is it a sum? Because the change in this with respect to kind of as it's coming in from that and that, you're able to just aggregate it. And the reason for that is essentially, I'm not going to talk this through really simply right now. Come to office hours and we can talk about it. Yeah. Yes.
So I know that PyTorch builds its computation graph dynamically. For instance, imagine that in your forward pass you have a conditional, which is if the magnitude of the gradient exceeds whatever, then I want to apply a clip operation. I have a slightly different use case for research, but do you know how it handles if you apply a non-torch operation to a tensor? If you apply some sort of UDF, which is just written using normal Python arguments, does it basically just suddenly say in the computation graph, anything, even if I use torch operators before that node in the graph, it is now not optimizable, and I'm just going to treat that basically as the way I would treat a data input, for instance?
So there might be hacks around this, but generally if you want to have any operation within a neural network defined in PyTorch, you have to define it as a torch operation, which is basically you are required to define a gradient for that operation, right? So you have to assume that everything's differentiable. And this is where things kind of get nasty, because if something doesn't have a simple gradient, so there's a lot of built-in stuff in PyTorch that handles what those approximations to those gradients would look like. But if you have something that's really complicated, for example, like an occupancy model of species, which is something that we work with, then you actually might have to define that as a torch operation. It also depends, sometimes there are kind of choices you can make based on whether or not that makes sense in the structure, right? You might not actually want to learn all the way through that thing if it becomes computationally intractable to calculate the gradient.
So I guess that's my question, is will PyTorch, if say you didn't define the gradient for that operation, or how to compute it, can PyTorch still optimize the rest of the model and just treat what comes in from the output of your UDF as basically being if you had input some x sub I, x sub basically a data vector?
I might just define that separately. I might define that as part of your pre-processing for your data, right? So the pre-processing steps don't necessarily need to be differentiable. Things like data augmentation. So you could put that UDF in your pre-processing, your data loader, and then whatever comes out of it would then be the data that you were going to optimize towards. That's probably the simplest thing to do. But again, computational complexity can get really nasty with some of this stuff. So maybe that's not too bad, but I've definitely run into issues where I've tried to build simple statistical models into machine learning, and with varying levels of success, and often it's just okay, it's technically possible, but it's intractable to actually learn. Yeah?
On this exact graph, for the superscript A and B, what do they really represent? Are they?
Oh, it's intended to be it's intended to be open-ended. So they could literally just be a duplicative copy of both, right? Or it could be some splitting of the embedding vector, or et cetera, et cetera. So it's any branching operation. Yeah, any differentiable branching operation. Okay, one last question. Yeah.
Problem set, is that supposed to be on Gradescope right now?
It will be there soon. I thought it was up already, but it's not.
3 p.m.
3 p.m. Okay. All right. Thank you guys so much. See you soon.